Hello everybody, this is the first video for chapter 2 of the statistical learning class. Sorry, chapter 3 of the statistical learning class. So the purpose of this chapter is to present a few prediction methods in a regression context. So we'll still discuss the k-nearest neighbors method introduced earlier in chapter 2, but we'll also mention linear models. So for instance, linear regression, and we'll also discuss how nonlinearities can be incorporated still using linear regression. And we'll also discuss model selection in the context of selection of predictors, and then we'll finish with regularization. Okay, so there's a lot of topics covered in this chapter. This chapter works mainly in a regression context, but some ideas, as we'll see in subsequent chapters, could be carried over to classification problems. So this chapter discusses parts of chapters 3 and 6 from the ISL textbook and chapter 3 from the more advanced ESL textbook. So let's recall what's a regression problem. In a regression problem, we have a training data set which contains small n observations. So each I is one of the observations, and yi is the response variable for observation I in the data, whereas xi is the set of predictors. So xi can be a vector if there are many predictors. So here xi will be denoted by xi1 until xip. So xi1 to xip are the p predictors associated with the ith observation. And here we're going to assume that yi and xi are quantitative. Okay, so we won't consider qualitative variables here. So ultimately, as we discussed in the earlier chapters, our goal would be to predict the response y0 for a totally new observation unseen in the data based on the value of its predictors x0. So as we've seen earlier, we could apply the k-nearest neighbors method that we've studied in chapter 2. So let's recall this. The black dots were our simulated data, which were basically simulated by taking the predictor cube plus a noise term, and we saw that the k-nearest neighbors method with k is equal to 3 gave this prediction. Okay, so this function here, the blue curve, represents the estimated prediction function f hat. Okay, so we see that f hat kind of picks up the pattern, but we see clear shortfalls with respect to this method. It's that the prediction doesn't vary very smoothly, whereas in practice many phenomena have a smooth variation with respect to the value of predictors. Okay, so at least the expected value of a random variable would vary smoothly. Maybe not the realized one, because realized responses, there's always noise, but when we make predictions are often related to the expected value, and the expected value should vary more smoothly. Okay, so as we saw in the plot, k-nearest neighbors produces piecewise constant functions for the prediction, which is non-smooth. So this can be problematic. So it's even discontinuous. So for many phenomena, as we said, it might be more reasonable to expect that the prediction should be a smooth function of predictors instead of a very bumpy and erratic one. Another issue associated with k-nearest neighbors is that it performs notoriously badly in some high dimensional problems. Okay, so what do we mean by high dimensional problems? It's when p, the number of predictors for each observation, is very large. Okay, so why is that the case? Why does k-nearest neighbor tend to perform poorly when the dimension of the predictor space is high? Well, let's provide an example. Okay, so let's say we have p predictors, so the vector of explanatory variables consists of x1 until xp, and let's assume that our predictors, all of them are independent uniform 0, 1 random variables. Okay, so x1 is between 0 and 1, xp is between 0 and 1, etc. So let's say we want to construct a hypercube in p dimension which covers 100% times r of the total volume of the hypercube 0, 1, 0 to the power p. This p here represents the Cartesian product, so it's the Cartesian product between 0 and 1, 0 and 1, 0 and 1, etc. Okay, so here the idea, so let's give the example in 2 dimensions just for illustrative purposes. So let's say p is equal to 2, then the volume of the predictor space is kind of the 0, 1 square here. So here that could be values for the first predictors, here values for the second predictor. So here, let's say we want to construct a hypercube in dimension p. So when p is equal to 2, this is simply a square, which covers 100 r%. Okay, so let's say r is equal to 1%. Okay, so let's say r is 1%, so 100% times r is still 1%. Okay, so so here this is the hypercube. So we'd like to construct a square here which covers an area of r times 100% of the total predictor space. So the question here is, what's the length of the edge of that hypercube you must consider to obtain that volume? Okay, so here let's consider this. Okay, so we'll okay, the idea, let's give the example in 1 dimension. Okay, so let's say r, let's go to the example first. So r, let's say it's 1%. So if you have a predictor space in 1 dimension, then your predictor falls on the straight line 0, 1. So if you want to find a hypercube in 1 dimension, so a segment of line which covers 1% of the total volume, then here, okay, you simply need to find a part of the straight line which has length 0.01. Now if p is equal to 2, what happens then, if you want to cover 1% of the area, then you'll need to find the square. But here the side of the square will not be 0.01 anymore, it will be 0.1. Okay, because 0.1 times 0.1, the total area would be 1%. So 1 over 100, which is 1% of the entire area. Okay, so we can see that if we want to cover 1% of the area, the larger the dimension space here, the larger the edge of the hypercube must be. So in 3 dimension, it would be larger. So if you calculate in 3 dimension what the length of the edge should be, it should be 0.21. And how do you do that? Well, you simply have to solve okay, so r is equal to s to the power p, okay, where s is the length of the edge, and if you multiply that p times, so because you're in p dimension, to find the length of the edge of your hypercube, which covers r, so 1% here, it should be 1% is equal to your edge length to the power p, because for example here, here the volume is 0.01, so p is equal to 1. Here in 2 dimension, the volume is 0.1 times 0.1. If you're in 3 dimension, it would be like your edge length to the power 3, etc. So if you solve that, then your edge length is simply S is equal to your percentage of the area or volume you want. Let's say in our case it's 1% to the power 1 over p. Okay, so you can make that calculation for various values of p, and then you get that when p is equal to 1 it's 0.1, when p is equal to 2 it would be p is equal to 1 it's 0.01, p is equal to 2 it's 0.1, p is equal to 3 it's 0.21, and if you continue like this in p dimensions, then the edge length become 63%. Okay. So what's the consequence of this? So if you're in 1 dimension, let's say the dimension space is very small, okay, to get 1% of the total area, you only have to consider values of the predictors, x1. So here I wrote x1 until xp, but since p is equal to 1, it's only x1, that are only 0.01 apart. Okay, so when you consider neighbors, they're very close to each other. Okay, so if you want to find an area where there's only 1% of the total volume is in 1 dimension is length, the predictors are very close to each other. Conversely, if you're in high dimension, then to get 1% of the total volume of the predictor space in 1 dimension, you need to consider edge length of 0.63%. So you need to have predictors that are 0.63% or 0.63 apart over a total range of 1. Okay, so some of them might be very far from each other. Okay, so let's illustrate this in, let's go back to 1 dimension and 2 dimension. That might be more clear. So in 1 dimension here, this is 0.01. In 2 dimension here, this is 0.1. So here, to get 1% of the volume in 1 dimension, the predictors must be very close to each other. But here, if you consider an area covering 1% of the total volume of the predictor space, you might have 2 observations here and here, and their predictors might not be 0.01 apart, but 0.1. And if you're in 10 dimension, then the edge length covers more than the half, so it's 0.63 over 1. So many predictors might be 0.63 apart, and you still, let's say all predictors are 0.63 apart, and you would still cover exactly 1% of the total volume. Okay, so because of that, the neighborhoods in high dimension, they're not so local anymore. Okay, so if you want to have k nearest neighbors, sometimes the nearest neighbors you obtain are very far away, because when you have 10 predictors, or if let's say you're in 10 dimension, the total predictor space will be very sparse, in the sense that you will have very few areas in the total volume that are visited by data point. So if you want to find close data points, then the closest one might still be very far away, and for some predictors they might be still very far away. Let's say 2 observations, which could be considered close, might have some predictors that are very far away, so they might not even be very relevant to predict each other. Okay, so this is the main issue with k nearest neighbors in high dimension, is that when you try to predict for a new point, if you look at the closest neighbor, while the closest neighbor might have some predictors that are very far away. Okay, so here in 10 dimension, it's more than half the range, the possible range of the predictor value. Okay, so when you do average across neighbors, some of the neighbors might be completely irrelevant because for some predictors, they might have values that are very far away. So for this reason, k-nearest neighbors might fail in high dimension. So we need other methods to be able to make sound predictions in high dimension. So traditionally, let's say 40 years ago or something like that, many statistical problems, they were applied in very small dimension contexts because the data we had was not as huge as today's data. Computer power was lower. So a lot of methods were developed to cope with low dimensional problems. But nowadays, with the very impressive amount of data we have, very large amount of data, it's very important that we develop methods able to cope with high dimensional problems. Okay, so we can see that k-nearest neighbors might not be your best choice if you want to tackle modern types of regression problems where with very high dimensional predictor spaces. Okay, so are there alternatives to k-nearest neighbors? Well, the answer is yes. So the first alternative that we could consider is the very well-known linear regression. Okay, so for this course, I expect most of you to already have a linear regression background and to have followed the course about this. If you didn't, it's not the end of the world, but you will have to go through the ISL textbook, and there's a chapter, I think it's chapter 3, which covers extensively linear regression. So you'll have to go through this chapter to understand the material here. Okay, so if you like that linear regression background, please take the time to go to the relevant chapter and the ISL textbook and read it so that you can understand what we're doing here. Okay, so I'll nevertheless summarize linear regression in its simplest form. So in a linear regression model, what we assume is that there's a linear relationship between the response that we're trying to predict and the predictors. Okay, so here we assume that the response is a constant beta 0 plus a linear combination, so sum across all predictors of beta j, so this is the coefficient for the jth predictor, times the jth predictor for observation I, plus here a noise term which represents deviations from that linear relationship. Okay, so here the beta 0 is known as the intercept. So in some models you can remove beta 0. Okay, so sometimes there is no beta 0. This is known as a regression without intercept, but often when we include that constant, this is known as the intercept. Plus here the betas, so the predictors, of course, they vary across observations, but the betas are common for all observations. Okay, so they represent the trends across all observations, and the beta j's are known as regression slopes. So the most common approach to determine parameters beta in a linear regression is through a methodology called least squares, okay, or ordinary least squares. So to do that, the idea is that for a given estimate of the betas, so beta 0 until beta p hat, so hat denotes estimates, we can form predictions of the response for a given observation. So the predicted response y I hat, predicted response for the ith observation could be its estimated intercept plus the sum of estimated slopes times the predictor for the ith observation. So this is for a fixed estimate of betas, and then what we want to do to determine these estimates of betas, we're trying to find the betas estimates such that which minimize the average squared prediction error within our training data set. Okay, so we average the response in our data set minus its associated predicted value based on these predictions here. So this is known as least squares because we try to find parameter estimates which minimize the sum or the average of square prediction errors. So least squares means we minimize squares. Okay, so a bit of notation here. Let's define beta as the column vector which contains beta 0 until beta p. So these are all model parameters. The training response vector y, which contains y1 until yn, which are the responses in the data set. And let's define the design matrix x, which is a matrix containing the predictors for all observation. Okay, so each row corresponds to an observation and each column corresponds to a given predictor. Okay, and here this column of 1 is why is it there? So here x1 until xp, these are the p predictors for observation 1, but then we might be wondering why is there that column of 1 here? So it's because 1 is the predictor associated with the intercept. Okay, so if we go back here, having beta 0 here is simply equivalent to write beta 0 times 1, so as to assume that there's a predictor also associated to beta 0, which is always equal to 1 for all observations. Okay, so here x represents what we call the design matrix, which contains all predictors for all observations, where each row represents an observation and each column represents a predictor. So as you've seen in your previous linear regression class, the solution to the well-studied ordinary least squares problem is given by the following. So the vector of parameter estimates is given by x transpose x inverse, where x is a design matrix, times x transpose y. Okay, so I won't rederive the steps right now here, but because first this result has already been derived in previous courses, but in case you are lacking that background, the proof is given in the exercises, so I invite you to do the exercises. Moreover, if you've already seen that result in previous classes, typically the way to show it is long and cumbersome. So you have to differentiate individually with respect to all the betas, come up with a system of equations and solve it like this. But in the exercises, the proof uses vectorial differentiation, and you can see that using these vectorial differentiation operators that we've defined in the preliminary slides, the proof becomes much easier to do. Okay, so it simplifies a lot calculations to use vector differentiation. So even if you've seen this result, please do that exercise again while using vector differentiation, so as to be comfortable with deriving these types of results in a much more seamless manner than if you had to use the traditional proof that is given in linear regression classes. Okay, so now this gives us the parameter estimates obtained from a training set, our original data set. So if there's a new observation whose predictor is x0, so x0 is a vector which contains x01 until x0p, all the predictors of the new observation x0, then the prediction can be formed as follow. So the prediction would be, okay, I'll write this one here. The prediction here would be the intercept hat plus the linear combination of slopes, estimated slopes, times each predictor of x. And this summation here, it can be written as the following vectorial product. So not vectorial, but sorry, matrix product. So here if you write 1x0, so here this is a vector, a row vector which concatenates the the 1 here, and here this row vector of all other predictors. So here this here, it's a row vector of dimension p plus 1. P plus 1 stands for the 1 here, which is the 1, and this guy is p dimensional, times the column vector of predictors. Okay, so this is the short way to represent this summation here, which is the linear combination of predictors weighted by the slopes plus the intercept. Okay, so in R, because in the class and assignments, you're going to have to use the R software extensively. So to apply linear regression with R, you can use the LM function. Okay, so the textbook offers examples. There's tons of examples online, but you should be at some point comfortable with the LM function being which allows you to apply linear regression. Or alternatively, if you're more comfortable, you can program linear regression yourself. If you use vectorial or matrix notation, it shouldn't be very complicated to like program that by yourself. Okay, so we said in high dimension, k-nearest neighbors might not be our favorite method. So then what happens with linear regression? Is it a good method? Well, it can be a good method provided that there's indeed a true linear relationship between the response and predictors. But when the relationship is not linear, then you might have inaccurate predictions. So for example, if we go back to our chapter 2 example, where the true pattern is the x cubed function, if we try to find to fit a straight line here, we see that the overall direction makes sense, but here our predictions would be inaccurate because we're unable to fully capture the curvature of the genuine pattern. Okay, so fitting a straight line to this might provide inaccurate results, especially at the endpoints here of the predictor space, where we can see there's underreaction to this curvature. Okay, so pure linear regression, it might work for some problems, but when there are nonlinear relationships, it might fail to produce accurate results. Okay, so this is on the bad side. It might be inaccurate if relationships are not linear. On the nice side, the good side, the linear regression always provides a smooth fit. Okay, so because of the smoothness, we don't have this very bumpy curve we had with k-nearest neighbors. Okay, so there are pros and cons with linear regression, as we can see here. Okay, so now one might be wondering, well, let's say I understand linear regression very well. I'm comfortable with that. So I'd like to use linear regression even in a context where there are nonlinear relationships between the response and the predictors. Is there a way to do that? And the answer is yes. So an approach to be able to do that is to apply transformations to the predictor and do regression not on the original predictors, but instead on transformations of the original predictors. Okay, so let's say we have capital K, which is a natural integer, and consider small k go from 1 to capital K. So I apologize here, there are many k's, so k nearest neighbors, k fold cross validation. So here, these small k and capital K, they're just not related to the previous k's we've discussed. Okay, so it's not related to k fold or k nearest neighbors, it's some other k. But for the various k's, we can consider a transformation called HK, which takes all predictors of an observation and return a real number. And we can consider capital K of such transformation. So H1 until H capital K. And then what we can consider instead is well, here I use the expression linear basis expansion, which will be a bit more justified here. But the idea here is our prediction function could be instead the intercept plus a linear combination not of the predictors, original predictors themselves, but of transformations of such predictors. Okay, so we're going to see that by applying such transformations, we can be able to capture nonlinear regression, nonlinear relationships between the original predictors and the response. Okay, so what are typical choices? Of course, these are not the only choices, but some typical choices for the transformations are the following. So one category of transformations are polynomials. So hk of x is equal to x if you're in one dimension, for example. So this, as we'll see shortly, this leads to what we call polynomial regression. Okay, so and it allows to capture polynomial relationships between a predictor and the response. Another common set of transformations are trigonometric transformations. So hk can be of the form sine of kx divided by 2 pi or cosine of kx divided by 2 pi. Okay, so this is a bit mysterious. Why would we consider trigonometric transformations? But we're going to see, or we're going to discuss, that such set of transformations can allow to capture a very large set of potential relationship shapes between the response and the predictors, which is due to what we call Fourier expansions of some functions. Okay, so to make a quick summary of the topic, it's because let's say we have a prediction function. Let's say that we have the true prediction function here, that is f of x. Well, if you use a Taylor expansion, then f of x can be, for example, f of x0 plus f prime, okay, evaluated at x0. I won't write it, so x minus x0 plus f prime prime x minus x0 squared divided by 2 or something like that, and plus etc. Okay, so you see that for a Taylor expansion, you can represent many functions as a polynomial of infinite degree. Okay, so you can see that yeah, so that's what I want to say. And conversely, if you use Fourier expansion, then f of x, I won't write the exact formula here, but it's okay. It can be approximately equal to a summation of sine or cosine. Let's write it like this: cosine of some constant ci times x. Okay, and here ai. So here, this is just in a nutshell. If you want to have a more accurate depiction of Fourier expansions, please go here. So here ai's and ci's are constants, which have to be suitably chosen. But the idea here is that you can express many functions as linear combinations of sines and cosine functions. So using these cosines or sine functions as predictors could allow you to recover these type of patterns or functions f, which drive the pattern associated with the responses. Okay, so this is why polynomials and trigonometric functions are very typical choices for transformations, is because such transformations allow recovering a very wide class of relationships between the response and the predictor. Okay, so if we consider, let's give the example of polynomial regression where hk is hk of x is x to the power k, then if we apply this, so here we consider hk of x is equal to x to the power k. So if we have that, then if we consider the previous model that we've discussed, we said that the model assumes the response is equal to an intercept plus a linear combinations, not of the original predictor x, but instead of all of its transformations. So here all of its transformation are basically powers of x. So here in that case, p would be equal to capital K. So sorry, here I think to be more consistent with what I wrote earlier, I should have put a capital K here instead of the lowercase p. Okay, so but here let's use lowercase p, but to be consistent with what I said, this should be capital K. So here we see that if we replace the hk by the powers, we have that the linear relationship indeed become truly a polynomial relationship. So you assume that yi is a polynomial of order p of the predictor plus epsilon I. Okay, so here we assume that we had a single original predictor x, and then the transformations we consider are the various polynomials of that predictor x. So here we can, because this is a linear model, we can use the linear regression solution we derived earlier, where here x to the power 1 to the power 2 until to the power k would be the capital K predictors in the linear regression. So if we put all these powers in the design matrix, we can get the solution, make our predictions, and we can see what we obtain here. Okay, so if we run polynomial regression on the data we've presented earlier, the black dots are still the observations. So we see that if we pick p is equal to 3, so if we take cubic regression, then the cubic function we obtain is very nice and represents very well the overall pattern. And this makes sense because we said we've simulated the original data with the cubic function plus a noise term. So if we run order 3 regression, then provided that the betas, estimated betas, are close to the true beta of the cubic function we use to simulate data, then we should have a very good fit, which makes sense. But now again, so if we saw that if we use p is equal to 1, we have some underfitting where the model is not flexible and you have a straight line which doesn't match very well the pattern. If you have just the right amount of flexibility, p is equal to 3, then you have this cubic function which matches observation quite well and captures the overall pattern. But then what happens if p is too large, so it is much larger than 3? Well, the idea is if, let's say, we use an order 15 polynomial, then you clearly have some overfitting. So the model is too flexible and try really to pass by the various points a bit too well. So we see that the model captures not only the genuine pattern, but it also captures the noise because it's too flexible. So this is undesirable. So once again, as we did for the k-nearest neighbors method, for polynomial regression, or even for regular linear regression, when you have several predictors, you need to find just the right amount of predictors so as to get enough flexibility to be able to fit the pattern well, so no underfitting, but not too many predictors, because if you have too many predictors, then the model is too flexible and it will capture noise and provide overfitting. So exactly as what happened with k-nearest neighbors, where you had to choose the capital K, which is the suitable number of nearest neighbors, here in polynomial regression, or even in regular linear regression, where you have many predictors, you need to find what's the suitable number of predictors I should use so that I strike the right trade-off between not enough flexibility and too much flexibility. Okay. So now, as we saw in the previous example, p is equal to 1 leads to underfitting, so it's not enough, it's unflexible. P being 15, it's too flexible, there's overfitting because the prediction curves look like this. So the question that arises is, how do we find a suitable P? So we'd like to find the answer 3 because it's the true answer for the genuine pattern. But how would we find such P which makes more sense? Well, the idea we can use is exactly as we did in chapter 2. We could have two data sets, one on which we train the data with observations and one on which we're going to validate our data. And so what we want to do is, for each individual P, we run the polynomial regression on the training data, use these to come up with f. So f, our prediction function, is indeed characterized by the beta hats. So we find beta hats from the training data, make predictions for the validation set, and then calculate the out of sample prediction mean square error, which is the mean square error which contains the average prediction errors made on the validation set. And so if you do that, you can do that for all P's. And if P is too small, then you'll have large out of sample errors because your model is not flexible and gives bad prediction. But if P is too large, then the predictions will be very bumpy. And although you will have very small training errors on your validation set, these bumps will not be helpful to make predictions. They will just worsen your predictions. So you'll also get a large validation error. So the suitable P, using out of sample MSE should be able to help you finding a suitable P which strikes the best predictive ability and avoids both underfitting and overfitting. Now, once again, if you don't have two different data sets, well, either you can take one data set and split it in two. So one part is for training, another part is for validation. Or, as we described in chapter 2, you can use cross-validation. So you take your data set, you split it into, let's say, k-fold or 10 folds, and then do the cross-validation as we've seen earlier, which maximizes the use of your data for performance assessment, because all data points are ultimately used in performance assessment and cross-validation. Okay, so cross-validation, it's not reserved to k-nearest neighbors. We could do that for also for other prediction methods. Okay, so one thing I want to mention here is that cross-validation, if you look in statistics, it's not so recent that it was extensively used in practice, because as we discussed, cross-validation methods, they can be very expensive in terms of computation, because if you use, for example, 10-fold cross-validation, you need to train the model 10 different times, whereas traditionally it was very expensive to sometimes train the model a single time, so you didn't want to repeat the training many times. So traditionally there were other criteria which were developed to assess the performance, which didn't rely on out of sample performance assessment. Okay, so several of such criteria were developed in the literature, such as maybe you know them, AIC, Akaike's criterion, corrected Akaike's criterion, Bayesian information criterion. But these, we'll talk about them in the subsequent video. So I'll stop here for now. Thanks for listening. I'll see you next time.